Okay, so let's now consider the force on current that experiences a magnetic field. So we know that a charged particle in a magnetic field experiences a force that looks like that, but charged particles, a collection of charged particles, is a current, and so we can think of turning this kind of expression into an expression for currents by considering little bits of charged particles that experience, therefore, a force that looks like this. Right, so a little bit of a tiny bit of charge, a particle with a tiny bit of charge dq experiences a tiny force that obeys this equation, and it looks like this because the charge is infinitesimally small. But we can turn this into an expression for current by recognizing that dV is equal to the time derivative of the position vector, dl dt, cross B. We could write this as dr dt if we want, but it's the same thing. And then we can just simply think of these as ratios and construct that kind of a thing and recognize that this thing is nothing more than what we mean by current, and so we get I dl cross B as our final expression. And so this means that the force on a current in a magnetic field looks like this. Okay, so we want to explore that idea. So let's imagine that we have two infinitely long current-carrying wires. There is a wire that carries current I1, and there's a wire below it that's also infinitely long that carries current I2, and they're both in the same direction, and maybe they are at a distance d apart. And so we want the force on each wire, or for that matter, the force at each point on each wire. So this is the expression that we need to evaluate. But notice that what we need, if we want the force, let's say, on this wire, then we are integrating along this wire. Every little dl is a little piece like that, say, and there's a current I2 going through there, and so the force on this little piece is going to depend on the magnetic field at this location. So we need to evaluate the magnetic field here, and that magnetic field is, of course, produced by this current, and so this wire feels a magnetic force due to the fact that there is a magnetic field produced by the current I1 above. So let's evaluate the magnetic field, B field, at wire 2. So let's call this wire 1 and this wire 2. And so we need the magnetic field at wire 2. And of course we know by, we could use Ampere's law and evaluate the field produced by this current at a distance d, right? So Ampere's law gives us the magnitude, B dot dl equals mu naught I enclosed. We can use that to find the field at a distance d below this wire, and everywhere it will be the same by symmetry. So when we do that, we're integrating on a path. This dl is not this path. It's not part of this path. It's part of a path that If we look at, if we put our face right here and we have the current I1 coming straight at us, and therefore we want the field at a distance d here below the wire, that means that the path of symmetry on which the magnetic field produced by the current I1 must be the same everywhere on at a distance d. So that's the path on which we're integrating, and the infinitely long current carrying wire that carries current I2 is going through here, right? It's coming out of the page there. That's where we want the magnetic field. It's everywhere the same along this straight line here, but that's the path on which we evaluate Ampere's law. What does it look like? Well, it looks like B. We're calling this B1 at a distance d, so it's 2 pi d because we're integrating on the circumference, and that gives us mu naught times I1 because the current enclosed is the current that's going through there. So we have the magnitude of the magnetic field at the location of wire 2, and it looks like this. Okay, so this needs to go into here, but we need it to be a vector. So let's plug this in. So let's write this expression. Force, let's call it force 2, force on wire 2, is equal to the integral. We're integrating over the second wire, so it's I2 dl2, right? We're integrating over little pieces of wire 2 from minus infinity to plus infinity in that direction, cross B1. And what does this look like? Well, the I2 is a constant, and the B1 value has a magnitude which doesn't change as we're integrating along here. So we get I2 times B1, which is mu naught I1 over 2 pi d. Then we're integrating. What we have left is just the dl2, but we also have a direction. So let's say we have a coordinate system where to the right is x and upwards is y, and the direction that we give to this quantity, or rather this quantity here, is the index finger is to the right, and the magnetic field here is given by the right-hand rule applied to that part of the Biot-Savart law that has I1 as the current. So dl, the current I1 is this way, and we want the field downwards. So my middle finger points to wire 2, and my thumb is pointing into the page. So the magnetic field, B1, at this location is pointing into the page. And so we have I2 this way to find now the direction of the force on wire 2. We have current flowing this way, dl2, cross B1, which is into the page, and so the thumb tells us that we have an upwards force. So the force at every point here is that way. That's the result of the vector product there. And so we simply have to integrate to get the force. Everything is a constant, so we get mu naught, pull out the mu naught in front, I1 times I2 over 2 pi d times the total length, which is actually infinite, times the j hat. So it's not surprising that the force is infinite because the wires are infinitely long. So it would be better to talk about the force per unit length, the force at every point, this way. That would be a finite quantity. So we can talk about F2 per unit length L, and that's mu naught I1 times I2 over 2 pi d, and it's in the upwards direction. And by symmetry, we could go through the entire argument and replace and do it for the top wire, right? So in that case, we would be integrating I1 dL1, and the field there is produced by the current I2, so we would replace this with B2, and we would, of course, end up getting, we can just look at the symmetry of the problem. The force would have to be downwards on this wire.